Hello students, welcome back. So let's revisit quasi-static process. As you understand this, quasi-static process is the process which is the only process which can be represented on a two-dimensional plane with continuous curve. Okay, right. Let's look at the a characteristic of quasi-static process. See, quasi-static process is also called as fully restricted process. Fully restricted process. And you can imagine why it is so. Because every time there is nearly equal and opposite force which is resisting this expansion. In this case, we are considering expansion. It could be true for other process. So there is a resistance, right? Because you are removing one slice and the inequilibrium force is infinitesimal. There is nearly equal opposing force. Okay, so it's called as fully restricted process. Now, what could be a polar opposite process to that of fully restricted process, to quasi-static process? What would be a polar opposite process? Pause this video and think about it and come back. Okay, welcome back. So, a polar opposite case to the fully restricted process is that of free expansion, zero resistance, right? Zero resistance, expansion which takes place without any resistance. That is the exact opposite, the polar opposite case of fully restricted. Now, how can we imagine that process? And something which we can, which is easy to imagine. Let's say that we have a compartment which is split into two halves, right? It's split, and this is the partition dividing this. Okay, so let's say that there is gas in this. So this is, I am showing the system boundary. This is gas and this is vacuum. This is vacuum, there is nothing inside. Okay, so the gas has got some pressure, some temperature, etc. So we can, so this is under thermodynamic equilibrium, and we can plot the point. Let's say this is the point. This is thermodynamic equilibrium state. That can be plotted over here. Fine. Now, if you remove this partition, right? You take out this partition. What would happen? The gas would expand. And remember, this is vacuum here. So the expansion is not resisted at all. There is zero resistance. So it would expand, and now you will we have removed this, and now the gas would occupy this full volume. So volume has increased, the pressure would drop, right? So a new equilibrium state would be arrived at. Now this new equilibrium state can be represented by a point. Let's say the point is here. Fine. But while this process was taking place, what was happening? The pressure in the gas was different at different points. The gas is expanding, so pressure is different at different points, right? The temperature could be different, right? So you find that while this is expanding, the entire space is filled up, the properties are changing. There is not a single value of property to represent the entire system. So there was no inequilibrium state. Okay, since there was no inequilibrium state, we couldn't represent that here, right? Unlike this, where every slice is removed and you get a new equilibrium state adjacent to the previous equilibrium state. That doesn't happen. So what you would have is first equilibrium state and second equilibrium state, and you are not able to trace the process here. Okay, you can approximately say that this is the dotted line, but that's an approximation. You can't, that doesn't represent truly the equilibrium, the process, because this process is not passing through infinite equilibrium states. Fine. Okay, so this is free expansion. Let's compare these two. Is this process a real process? Is it possible? No, it's not possible. Is this process a real process? Is this possible? Obviously, free expansion is a real process, right? This is not. This is an ideal process. Fine. Now let's do one more thought experiment. let's say that, let's bring this back. The gas is, imagine the gas is in the first chamber. This is again vacuum here. So what we do now is we are splitting this vacuum by inserting partitions in it, right? And let's imagine them to be infinite. So in a way we are, when I say the word infinite, we are certainly, this becomes a non-real thing, but it's a thought experiment. So let's say that we are splitting this entire vacuum by inserting infinite partitions. That means you have a small space which contains vacuum, and there are infinite such vacuum spaces. Okay. Now let's say that we remove. So this is our first partition. The gas is at certain pressure, certain volume, right? And then we remove the first partition. Let's say I remove this first partition. When you remove first partition, the gas would expand, right? Of course, the first state, let me say here, the first state of the gas is this. Then we remove the partition, the gas would expand, right? And when it expands, it would expand by infinitesimal amount. The pressure would drop by infinitesimal amount, and a new thermodynamic equilibrium state is arrived at. That means the new equilibrium state is adjacent to this. Then we remove the second partition. Again the gas would expand by infinitesimal amount, the pressure would drop by infinitesimal amount, and you have a next equilibrium state. Like that, if you keep on removing the partitions one after the other, you would get a continuous curve, right? Sorry. This is a continuous curve. Fine. Now see, what has happened? Is this expansion different from the previous expansion? It's not really, because we are saying that it's free expansion. Isn't it free expansion? Yes, it is free expansion. When you remove the partition, there is vacuum, a small space, infinitesimally small width, that vacuum, and the gas expands, right? So it's free expansion. It's not resisted. Again you remove the slice, again it expands. So during the expansion there was no resistance because it was expanding against the vacuum. So you get a continuous curve. The question is that if area under this curve, will it represent work? By the way, I forgot to tell, but this is something I assume you know, that area under the curve which we drew by removing the slice of piston, that was the work done, right? So similarly, because there is some work done here, it's expanded. So here is also expansion taking place, and that is represented by continuous line. Now would you say that the area under the curve will represent work done? Is there work transfer? Pause the video, think about it, and come back. Okay, welcome back. If you say that there is indeed work transfer, then you are wrong. Why you are wrong? Because for the work to be transferred, you need some resistance. Here, this is free expansion. Although you are able to plot this by imagining the entire vacuum to be split into infinite small vacuum spaces, the work done is zero, because every time the gas is expanded against zero resistance, for the work transfer there has to be some resistance. Okay, so this thought experiment would enable us to plot a continuous line to show continuous curve to show the expansion process. This is a thought experiment. This can't be really, but it under no circumstances you should say that there is work transfer here, because this expansion is not resisted. Okay, thank you.